Hi everyone, and welcome to this session where we will put a spotlight on the project Smart Urban Traffic Zones and also talk about how geofencing can be used to improve the road transport system of a city, and especially in regards to vulnerable road users. My name is Felicia Hökars.
And my name is Anna-Karin Salmi.
Yeah, and we are the project lead team of this project, and we'll take you through today's session. We have a Q&A function, so if you have questions, please send us them, and we will try to answer them at the end of the session. So before we go into what we are doing in this project, let's start with why we are doing it. And what are the reasoning behind testing smart traffic zones in the urban environment?
Yes, well, the transport sector plays a crucial part in achieving a sustainable society. But traditionally, road transport has also had a negative impact on health, mainly due to emissions and traffic accidents. So for this reason, action within the road transport system is integrated in several sub-goals of the UN Sustainable Development Goals. For instance, halving the number of fatalities and severe injuries in road traffic is part of sub-goal number 3, good health and well-being, while providing affordable, safe, accessible and sustainable transport systems for all in the cities while paying special attention to the vulnerable road users is part of sub-goal number 11, sustainable cities and communities. So these issues are very important for actors within the transport system to address jointly. And the digital transformation provides us now with new opportunities and tools to improve the transport system. And smart urban traffic zones will in the future be part of enabling a more flexible city where vehicles move on people's terms. During the years 2020 to 2022, this project has been testing different elements of what will be this powerful tool based on geofencing to contribute to quieter, safer, healthier environments in which we all can live.
Yes, and now to introduce you to the project, we will now play a short film, and thereafter we will go more into detail in the specific use cases that we are testing in this project. But let me just put up the film a moment here.
And while Felicia is changing the presentation mode here, let me just mention beforehand that we know that there might be some issues with this film, depending on your internet connection. So if it's a bit slow or if it's a bit out of sync, please apologize in advance and please bear with us. It's about 2 minutes long, and it can also be found on YouTube if you would like to see it after this meeting again.
By using geofencing, a tool to digitally define a geographical area and rules for vehicles to follow, it is possible to create more flexible cities where vehicles move on people's terms. In the project Smart Urban Traffic Zones, 3 concepts of smart zones based on geofencing are demonstrated and evaluated. At Hornsgatan in Stockholm, dynamically speed-controlled distribution vehicles are tested. Smart sensors are measuring the amount of people in the street, allowing near real-time speed reduction of the vehicles to calm the traffic and increase road safety. With speed and route-controlled heavy-mass vehicles, it may be possible to allow heavier transportation vehicles within the city boundaries of Stockholm. If the vehicles can load more concrete in their tanks, fewer trips are needed to the construction site, which will decrease the total number of heavy mass transports and help create a better urban environment. Construction site exits are possible risk zones for collisions. In Gothenburg, smart exits with connected sensors and digital warning signals are tested. This to increase safety for cyclists passing by. To implement the smart zone concepts, a scalable system architecture is used, allowing the vehicles and sensors to receive information and respond to the defined geofences. The project Smart Urban Traffic Zones is also investigating and evaluating the system effects, business models and regulatory frameworks to enable a future implementation of the geofencing solutions.
So that was that short film. I hope it worked for all of you. And we are now going back to our PowerPoint presentation.
Yeah, I hope you all see it now.
Yes, I see it, so it should be fine. So as it was mentioned here in the film as well, geofencing is at the heart of the Smart Urban Traffic Zones project. So it is of course useful to have a general idea of what geofencing is. A geofence is a digitally defined area where vehicles are controlled by digitally set rules, which then enables the control of how a vehicle is driven within this zone without human intervention. And in our 3 pilots, we are demonstrating geofencing applications focusing on speed reduction of heavy vehicles in the city, as well as activation of warning mechanisms within a smart zone aimed at vehicles and cyclists. And to achieve this, we are also integrating smart sensors in 2 of our 3 demonstrations. So this means that we are testing geofences that are static, dynamic, and smart, which makes this project unique in the Swedish national context, but also in an international context. So with this information as a backdrop, let's now take a closer look at our demonstrations and share with you some of our early results.
Yes, and yeah, let us start with the first pilot, Innovation Zone Hornsgatan. This pilot takes place on in one of the central parts of Stockholm called Södermalm. The geofencing zone is covering the street Hornsgatan and a couple of side streets to that street. Here, we are demonstrating geofence through smart speed limitation of distribution vehicles, as you could see in the film, and they are delivering groceries to stores and restaurants in this area. Around Hornsgatan, we have schools, restaurants, shops, and it's also close to a metro station. So this means pedestrians, cyclists, cars, and other modes of transport need to share the space together. So here, we have smart sensors that have been installed to measure the number of pedestrians moving in the area. And when the number of pedestrians detected by the sensor reach a predefined limit, a speed reduction is communicated via the geofencing solution to the distribution vehicles. This to calm the traffic and increase safety for people walking in the area. When the geofencing is activated, the speed of the vehicle is lowered from 50 or 30 kilometers per hour down to 20 kilometers per hour. So this means that the vehicles will not be able to accelerate above this new lower speed limit within the geofencing zone, unless the driver actively overrides the system by using a kickback function linked to the gas pedal. And in total, we have 6 distribution vehicles participating in this test. Yeah, and this pilot also includes a sensor aimed at tracking a loading zone on the street. This application is not directly linked to geofencing, but may act as a planning tool and an incentive in a future scale-up of the geofencing solution. So if the driver of the vehicle can receive real-time information on a specific loading zone to see if it is available or occupied, the driver may plan his or her route accordingly and avoid circulating the area while looking for available space. Which will also contribute to improved road safety and lower emissions. Also, the city can use this information to evaluate how the zone is used and issue tickets for unauthorized parking in the zone.
And this pilot has run from September to December of last year, 2021. The original plan was to run this pilot for only 4 weeks, but due to a very positive experience from all involved partners, and also a need to calibrate the threshold levels of the sensors detecting the pedestrians in the area, it was decided that this pilot should be extended. And the participating drivers has mainly had a positive outlook on their participation and on the pilot. But we have also seen that an unexpected large number of vehicles have had a higher speed than the speed reduction communicated by the geofence. So the project will of course make an effort to analyze this particular outcome and present it in our final report. One early theory of the reason behind this is that the geofenced area might actually have been a bit too small. So the vehicle may not have had the sufficient time to reduce its speed. And this is since the geofence works so that the ability to increase the speed is limited and the vehicle is not actively braking while entering the zone. But so far, all in all, this pilot has been a success story, and there are several interesting use cases that could be implemented on a larger scale. And in this final stage of the project, we will analyze issues related to the scale-up, including how smart sensors can be used to measure the density of pedestrians over a larger geofencing zone, and also how these sensors aimed at loading zones can be incorporated into a business case, both for the city and for the distribution companies.
Okay, so the second pilot of the Smart Urban Traffic Zone is demonstrating increased load efficiency of heavy mass transport through speed limitations. This demonstration takes place in Stockholm and also the area of Södermalm, with a geofence extending over almost the whole island. So that's a bit different from the innovation zone Hornsgatan, which is much smaller geofencing zone. This pilot includes one heavy mass transport vehicle and delivers concrete to construction sites in the Södermalm area. Under normal conditions, it is not allowed to load this vehicle with concrete to its full capacity due to limitations of the bearing capacity of the road infrastructure in this area. So to be able to to increase the load factor and in that way increase the transport efficiency, this pilot is demonstrating a geofence solution to reduce the speed of the vehicle from 30 to 15 kilometers per hour when entering the geofencing zone. The main idea is that a lower speed compensates for a heavier load of the vehicle and will thereby not have a negative impact in the road infrastructure. During the planned demo that we have in February, we plan to verify this assumption by following up and comparing vibrations that are transmitted into the road infrastructure from the vehicle in a normal speed and a reduced load versus a vehicle with a lower speed and a heavier load. This pilot, it's dependent on the city issuing an exemption to be able to carry a heavier load than it's currently allowed. This exemption is digitally issued, and the geofencing solution is used to ensure that the vehicle actually lowers speed when entering the area of Södermalm. So, yeah, and the technical basis for this geofencing solution is the same as is used in the previously mentioned pilot, the innovation zone Hornsgatan. The technical setup of the geofence was verified in the spring of 2021 using the test vehicle in the in a controlled environment around the concrete factory in the southern part of Stockholm.
And unfortunately, this pilot demonstration is a bit delayed due to some issues with the warning sign that needs to be mounted on the backside of the vehicle. And these signs need them to be activated when the vehicle enters the geofencing zone in order to warn surrounding traffic of the lower speed level, since this vehicle then actually becomes a slow-moving vehicle. And we do hope that this pilot will go live in the near future in February of this year. And even though it has not been yet demonstrated in a real traffic situation, we can already tell that the technical solution that enables the geofence works, since it's actually the same system that has been deployed in the pilot on Hornsgatan. And within smart urban traffic zones, we're not only aiming at demonstrating the pilot, but also analyzing possible opportunities and challenges to consider when scaling up the solutions. And since this case is enabled by the exemptions that allows a heavier load, as Felicia mentioned earlier, the legislations and practices regarding how and when such exemptions can be issued are also key issues to analyze. And this implies that to allow for a large-scale implementation of this solution, it might not be feasible to rely on exemptions. And there may be a need to develop the local regulations so that geofenced vehicles are allowed a heavier load under the condition that they reduce their speed or employ other solutions to ensure minimal negative impact on the road infrastructure and the surrounding built environment.
Okay, last but not least, the third pilot, safe construction site exits. This one is demonstrated in Gothenburg, as seen on the map. And in the upper right corner of the map, you can see the test site. This is an industrial area of Gothenburg with a lot of heavy vehicles driving in the area. So this is a good place to start testing this kind of solution. So this pilot aims at creating a smart zones at construction site exits to increase safety and reduce collision risk between construction transport and vulnerable road user, and in this specific case, cyclists. This is achieved by using connected sensors detecting the vehicle and cyclists passing by the construction site exit, and a warning system connected to a digital message sign notifying the cyclists to pay extra attention when approaching the construction site exit. The setup is shown in this picture. And in the lower right corner here is a photo from the demonstrations that was carried out this past summer. And this pilot has been carried out in 3 stages of live demonstrations. The first stage was a technical test in a controlled environment to test a technical solution that integrated the input from the smart sensors, detecting both vehicles and cyclists, with the variable message sign used to convey the warning message. The second stage was a test aimed at evaluating the behavior and experience of cyclists when interacting with the solution. The last stage of demonstration will take place in the end of January this year, and will examine the behavior and experiences of the drivers, drivers of the transportation vehicles, basically.
And even though all 3 stages of demonstration are not yet complete, we already have some results and conclusions from the previous 2 stages that we can share with you today. And in the live demonstration aimed at the cyclist experience, it was evident that the tolerance levels for delays or latency in the signal between the smart sensors and the variable message sign is very low. And it was therefore not possible to run the system as a cloud-based solution as we originally planned this. So a new technical solution that runs on location is now being developed and will be used in the 3rd stage of the demonstration. The cyclists that took part in the demonstration were all used to biking in a city environment, and they were interviewed about their experiences during the pilot. And these interviews show that the perceived safety of the cyclist increased significantly with the smart warning system in place, particularly in the situation where the vehicle was entering the construction site by means of a right-hand turn and then intersecting the path of the cyclist. And this is the situation that you can see on the photo here from the live demonstration. However, the cyclist also became more uncertain of who has the right of way at the construction site exits with the warning system in place compared to without it. It was also more common for the cyclist to stop at the construction site exit when the warning system was in place. And if this was a consequence of this increased uncertainty of who actually has the right of way has not yet been analyzed in detail. And the cyclist was also asked what issues they experience with the warning sign system and how it can be improved. And the most common answer to this question was that it was unclear what action they were expected to take based on the information on the variable message sign. And this was especially then in the situation when a vehicle was exiting the site, so the opposite situation from that you see on the photo. They also commented on the fact that it could be difficult to interpret the message and to understand who the message was directed to. And the main areas for improvement that was mentioned was also related to the information on the signs and the design of the signs itself. Regarding how the signs were placed, it was said to be important to have sufficient time to both read, process, and act on the information that was conveyed by the message sign. And it's also essential that you do not obstruct the line of sight and the possibility to have an eye contact with the driver of the vehicle.
Okay, so yeah, to conclude this run through of the pilots, we have summarized some of the key characteristics, that's a hard word, of the technical setup on this slide. And as we mentioned, the project is still ongoing, but the main parts of the demonstration have either already been carried out or are planned for in the near future. So the next step ahead is to continue to analyze the results and experience from the demonstrations in order to describe how the pilot solution may be deployed on a larger scale and look into how to tackle obstacles and unresolved questions.
But we do already have some lessons learned that would need to be addressed to enable a scale up. And apart from the dependency on exemptions that we mentioned in relation to the pilot on the concrete transports in Stockholm, one main issue that we have identified is how data is handled and the privacy of the drivers of the geofence vehicles. Since one main component in this pilot are speed reduction of vehicles during specified circumstances, it is necessary to somehow monitor the speed of the vehicle in some capacity. And this can become problematic if the driver is exceeding the allowed speed limits and thereby violating the regulations. This is information that the road infrastructure manager in Sweden is not allowed to process. It is a matter for the police authority to follow up on compliance with speed limitations. So this can also be a gray area whether a company is actually allowed to follow this kind of behavior from the drivers that they employ. And it is necessary to separate this information from the individual driver and vehicle somewhere in the data processing. The stakeholders and actors that are responsible for or affected by the geofencing zone are quite diverse and make up a complex network. And the cities are among the stakeholders that are responsible for the geofencing solutions, along with the service providers. And transport providers in our demonstration, mainly different type of delivery services. They also play a crucial part in setting up the geofences and are the sole actors in charge of realizing the impact on the geofence. And this is mainly due to the fact that the realization of the geofence is actually taking place in the integrated systems of the vehicle themselves. Other road users, such as pedestrians, cyclists, other car drivers, etc., are of course also affected by the smart zones and the behavior of the geofenced vehicles to different degrees. And how they are affected also depend on different factors, for example, on how vulnerable they are as road users. So based on these characteristics, stakeholders and actors will play different roles in value realization and have different perspectives on the smart zones and their impact in the urban environment. And this is now being explored in this project through a series of workshops and interviews. And if we can say so ourselves, it's quite interesting work since this perspective of value realization and business models connected to the pilots have not played a significant role in other geofencing pilots and projects so far. So we are very much looking forward to the final results of this analysis.
Yeah. So smart urban traffic zones has brought together cities, the automated industry, freight forwarders, technology providers, academia, and also public authorities to test different types of smart zones. And the wide scope of this project team has been a success factor so far, we would say, and the project would not have been able to take place without this collaborative effort. The project is ongoing until September this year, and it's a total budget of just under 40 million kronor. It's approximately 140,000 euros. It's partly funded by Vinnova's challenge-driven innovation program, and we are currently in a stage 2 project within this program. So next step is to look ahead to a stage 3 to enable further scaling of the solution tested in the today's mentioned pilots.
And well, if you are interested in knowing more about this project or in future collaborations with any of our partners, please do not hesitate to get in touch. Our contact information is here on this last slide. It is also available on the project website, which you can find a link here on the presentation as well. And you can also find our contact details on the Sweden Innovation Days website. And all information related to this project, including the final report, films, etc., is continuously published on the project website.
Okay, perfect. Thank you.